Welcome back. I want to make just a couple of quick notes about capacitors, just to tie this subject up before we move on to something else. Really, I want you to make sure that you know how to calculate equivalent capacitance, which is outlined in both of your textbooks. But basically, if I have more than one capacitor that's in a circuit, I can usually find an effective way to describe those two capacitors as a system. For example, if I have two capacitors in series, like we see in the top diagram, what is common between these two capacitors is the fact that the charge on the left capacitor is equal to the charge on the right capacitor, and therefore I can find out how these capacitors act together if I remember that the charge is exactly the same on each of the two. And so when I write down the capacitive equivalence of this circuit element, I have to use that as my starting point for understanding what the equivalent capacitance looks like. On the other hand, if I have two capacitors in parallel, it's not the charge that's the same between the two capacitors, but it's the potential difference across those two capacitors that end up being the same, because after all, they're connected by wires. The last thing I want to talk about capacitors is an interesting thing that we can find from the energy that's actually stored in the capacitors. So every time I take my capacitor and I hook it up to a battery, charges are going to be moved one at a time, but basically continuously, as I apply a potential difference across the capacitors. So the first charge is going to have to cross that potential difference, the second charge is going to have to cross that potential difference, etc., etc., etc. So if I want to study the energy that's built up in this capacitor, I now have to study what amount of energy does it take for me to move each of those charges one at a time across the two plates. So a little bit of energy is going to be equal to the potential difference across the capacitor times how much charge I'm moving, which I'm calling dq. And of course, I can always use the identity of the capacitor, that the charge on the capacitor is equal to the capacitance times the potential difference, to write this as Q, the amount of charge that's currently on the capacitor, divided by its capacitance times dq. So I can then integrate this to find the total energy, which is just going to be the integral of du, which is the integral of q prime over c dq prime from 0 to the total charge built up on the capacitor, which is 1/2 c times delta v squared, when again I've used the identity that the charge q is equal to the capacitance times delta v. And what's interesting about this particular expression is now I have a delta v squared that's built into my expression for how much energy there is in the capacitor. And that's pretty surprising. But I can take that one step further, because after I've defined how much energy there is in the capacitor, I can now talk about how much energy density is there inside the capacitor. That is, I know the total amount of energy. Can I find it as a function of the volume of the capacitor? And when I do that, I'm now taking little u to be the total energy, big U, divided by V, plug in what I got from the last slide, divided by the volume of the capacitor, which is the area of the plates in this example times the distance between them. I can then use the fact that I have a parallel plate capacitor to rewrite that in terms of delta V over d squared times epsilon naught over 2. And then I'm left with this expression that the energy density of the capacitor is equal to 1/2 times epsilon naught times the magnitude of the electric field squared. And this expression is really interesting, because it actually says that the energy that I've stored in the capacitor, that is all of the potential energy that I've gotten from moving charges one at a time across the potential difference, all of that energy is now stored in the electric field. And so the electric field, which up until now is just a purely mathematical object, seems to itself contain a lot of energy density.